Well, thanks, Harvey, and to the organizers for including us in this program. We'll be presenting some work being done under the Loop 3D project that Laurent introduced. Myself and Steve Richard will present. Just to check to see if Steve is here. Steve, are you here? Okay, it's still very early in Tucson, Arizona, so maybe Steve hasn't made it. In any case, we're presenting on a project and product called GeoScience Ontology. And as I mentioned, it's part of a broader piece of work under the Loop 3D project for developing an overall geoscience knowledge management system to augment 3D geological modeling. A key component of that knowledge system is the GeoScience Ontology, which is a way to organize and manage the knowledge. And the overall purpose of the GeoScience Ontology is to create a framework to represent any type of geoscience knowledge. So to cover the full spectrum of things that are possible to discuss geologically. Which is a very ambitious task, as you might imagine. And it draws its focus, well, we can see it as two parts. One part is focusing on the concepts inherent in geology, and the other is in encoding those concepts in some machine readable and processable language. Now, luckily, current tools allows us to combine those two aspects. But the focus of this work is primarily on trying to understand what the concepts underlying geology are from a particularly informatics and ontological point of view. So there's been a lot of work done over the last 20 years in representing geology digitally. And there's at the same time been a tremendous work done in information science, particularly in ontologies and the semantic web, on how to represent knowledge generally. And the idea behind this work, which is, I should add, a research initiative, not a standards initiative. So we were primarily looking at trying to combine those two things from a research perspective to see how they would fit together. So trying to adapt new methods of ontological analysis and structuring to what we already know about structuring geological knowledge. And what we've come up with is this geoscience ontology, which starts from a very broad basis on the most common things that exist anywhere in any domain, and then add a geology layer, and then certain modules. The geology layer contains the things that are most intrinsic to geology, and the modules are then specific elaborations of those, which may have been called vocabularies in the past. Predecessors to this work involve the early work in GeoSci-ML and some early ontology work, and then there's a certain amount of ongoing work right now amongst 2 or 3 different groups towards the same thing, which is more of a general ontological framework for representing geology. We fit into this general environment, primarily with differences on the ontological analysis. The particular analysis of how to structure the geological concepts is really what differs some of these ongoing and simultaneous efforts. The thing that always comes up within the CGI group is the distinction between GeoSci-ML and GSO, and I think Eric Brodaric did a really good job of explaining that one is aimed towards a transport schema and the other really is aimed more towards the underlying concepts inherent in geology. But from the point of view of development, let's say, of XML-based schemas, you can view the ontology really as the conceptual schema from which the other schemas are derived. And so the focus of this work really is on reinterpreting the fundamental concepts in an informatics way for purposes of representing geology. But one of the benefits of using some of these new technologies, or the newer ontology and semantic web and knowledge graph technologies, is that not only is there a particular conceptual can a particular schema be created, sorry, but also it can be serialized. So in fact, it could be potentially used as a transport schema because it can be serialized in a particular language. In this case, we've been focusing on the OWL2 language and various variants of that. And just in terms of the requirements for this ontology, well, it had to be both broad and deep. So we want to capture all kinds of, every particular kind of geological knowledge, but also have enough content there that it can be useful for encoding knowledge. So breadth and depth, modularization, we already talked about, allowing, building a certain framework, but allowing it to be easily extended for particular core modules. Nick was calling those vocabularies, but I like to refer to them more as modules. One of the things that also came around was being standalone. Now we've relaxed this a little bit, but initially we wanted to make sure that it doesn't necessarily involve too many other external linkages, only because sometimes they create logical inconsistencies creep in, which would then have problems, for instance, in reasoning. So it was the method of development is through a GitHub with a focus on the underlying analysis using various aspects of first order logic representation, but also foundational upper level ontologies as the basis for the utmost upper level, and then extending that into geological concepts through UML, OWL examples and testing and implementation. So what the overall structure looks like is a common layer that represents the things that are shared across any domain. So concepts like object, matter, process, event, space, time form the upper layer. The geology layer then specializes the upper layer for specific types of geological objects, geological materials, geological processes, etc. And then we have certain modules, which then are the elaborations of those. So particular types of geological materials, or particular types of geological processes, or particular types of geological events. And those would normally have been treated as external vocabulary or thesaurus lists. But in an ontological framework, these are all just more extensions of the more general framework. So we have this layered layer cake ontology versus layer cake geology approach to the development of the ontology. In terms of its actual organization with files, each of these have separate files. So there's one common file, and you can see in the common file that it consists of about 100 classes, for example. And then it leads to the general geology layer, which really adds 40 more classes to it. So there are only, in this case, around 40 core classes to represent geology generally. But then there are an infinite number of modules that specialize those classes. Currently, we have somewhere close to 40 different modules built largely on the vocabularies of GeoSciML. But you can see that the number of axioms grow because, and I should explain axioms, consider axiom as a simple type of rule, because these languages are all rule-based that represent this. And so, for instance, in the common layer, there's about 1,000 axioms. In the geology layer, adds about 200 or 300 axioms. But when we start adding all the modules, we're now up to 120,000 axioms. That all need to be resolved logically and be self-consistent. And we're still working a little bit towards self-consistency right now. There's still some consistency issues logically to be sorted out when we bring all those modules together. But it starts becoming a very large thing, as you can imagine, trying to represent the whole knowledge base for geology. And this is just the concepts of the geology. This isn't even the actual instance of those concepts. So having, for instance, the concept of a geological unit would be in this. Particular geological units and a catalog of particular geological units, for example, wouldn't even be included in this 120,000 set of axioms. That would be separate modules that would be instances of basic concepts. So, geology is large and complex, effectively. Now, to give you a flavor of a little bit about the ontological analysis, because this is really the focus of this work, is to try and understand the core concepts ontologically. And what that means is that understand essentially what the logical basis of basic geological concepts is, and then structuring those so that we can use those as a means of digital processing within a computer system. So we take a look, and I'll discuss 2 or 3 of them just for sake of example here: geological objects, geologic time, geologic structures. Will be, I think, the main focuses. Geological objects, well, there's nothing special here in terms of the interpretation. Geologic objects are things that are constituted by, solid or fluid geological materials. Rock objects are primarily solid materials. But where we get into a little bit more of the analysis is a specific rock object versus geological unit as 2 basic categories. Now, I should add that all this analysis should align with geological understanding. So we're not trying to redefine anything geologically. We're trying to take those geological understandings and analyze them in terms of ontological logic. So one big distinction is between, for instance, specific objects and geologic units. A specific object is something that's not contextual and it's not fragmented. So it's a single object, and that object, if you move it out of its context, so let's say to a different planet, would still retain identity. So a particular boulder or crystal or fossil would still be the same material, it would be the same boulder, crystal, or fossil on Earth as it would be on Mars. Whereas, geological units are things that are either fragmented or contextual, which essentially means whether they're stratigraphic or non-stratigraphic geologically. So stratigraphic things are contextual. If you take a particular formation and you move it to Mars, it wouldn't be the same formation. The stratigraphy would be different. Whereas take something like the geological unit composed of volcanic rocks, so just volcanic rocks anywhere, would be something that is fragmented, but it's not contextual because it's not limited to a particular set of relationships to surrounding rocks. It's just any volcanic unit, any volcanic rock would be part of the unit of volcanic rocks, for example. So these are some core understandings. They align with what we know geologically, but this notion of dependence on context and solidity, or fragmentation, are the underlying ideas that are used to structure this digitally. If we move on, similarly, the issue with geologic structures and trying to understand them is that geologically, there's an understanding that geological structures are derivative from their host rock bodies. But in what sense are they derivative? Can we capture that notion of derivation for a geological structure so that it can be useful in terms of representation digitally and informatically? And so we've come up essentially with a new theory of what's called features, which are these derivative entities of which geological structures are a type of, which eventually says that structures and features are derivative entities. They're dependent on host things, in this case, host rock bodies, and something else, and they're tied together by a relation. So for instance, and there's various kinds. There's folds that are derived from particular properties, like the shape of something, derived from a particular pattern, like a mineral lineation, or the fact that they have particular parts, or for instance, that such as a contact or a fault, they're dependent on certain rock bodies and the relationship between those rock bodies. So these nature of these dependencies is what underlies the notion of something being derived from a rock body. And it's a tricky concept, but I think we've come up with a good working interpretation for that. The interesting thing, and Steve, if you're here, you can take over at this point. Steve? No, well, I'll just keep going then. The interesting thing is that we've also analyzed geologic time as being a derivative entity analogous to geologic structure, but not exactly the same, obviously, because the notion of geologic time, of course, aligns with what we know geologically, but we've tried to capture that geological knowledge into a more of a digital framework, and that is that it's the relationship between notions of time and the rock record. So all notions of geologic time are somehow tied back to the rock record, and specifically the way that they're tied back differs. And that's, we've tried to capture that very tightly within the ontology. And it's led to, for instance, some fundamental concepts related to, for instance, geological time points, boundaries, and intervals. And within intervals, what Nick was discussing earlier, we've been trying to model very seriously, and that is the difference between generic and specific time units, as we've calling them. So Jurassic as a concept, and then Jurassic 2017 is a separate concept, and what the relationships between there are. And we have a theory for how those relations are modeled and what these are specifically. And then there are many other things, geological processes, events, and other things that have been analyzed in the same types of ways. But the last category I'll briefly discuss are geological relations, which we model right now as specific combinations of temporal and spatial relationships. So there are different types of relationships amongst temporal entities, how different time entities can be related before, after, during, and the way that spatial entities relate to one another, inside, outside, overlapping, etc. And the theory here is that if you take specific geological relationships, they are a combination of spatial and temporal relationships of these basic ones, plus some added rules and types from the ontology that geologically constrain those. So we have a very simple preliminary ontology of geologic relations based on these core concepts that's evolving. So what does this all this ontological analysis means? Well, firstly, what it means is that we have a very, because geology is complex, we have a very complex digital structure to represent it. And hopefully in the future that might get simplified for particular applications, but currently we're trying to look at modeling everything, which means it's probably more complex than it will be for all applications. But it does mean that we have a certain language in which we can then therefore represent this. So if we take an example of a geologic unit as on screen, the encoding within the ontology would be on the right. So take a particular geological unit, such as that green Jurassic unit in the middle, and you can see it's a formation from the lower Jurassic time period, and it has two parts, an upper and a lower part, and it has a top and a bottom surface, and has a thickness from thin to medium. And this is all falls out of the ontological analysis. This is the syntax that falls out of it. And it looks fairly straightforward, which is a good thing. It should, for example. If we move to timescale, then the timescale encodings are very similar to the existing ones, with the addition that there's as I mentioned, some more attention being paid to both where the data came for representing the timescale, so how you can connect that to the underlying observations, as well as the key things like GSSPs, etc., but also the ties to the rock record and how that's established as a sort of dependency. You know, time intervals can be related through time relationships, and then there are also relationships to the underlying rocks, such as the chronostratigraphic unit used to represent a particular chronologic time unit. Won't get into the details, but there's a lot of effort been here to look at this very closely and test it with existing timescales. And Steve's been working, he'll probably want to mention, on mapping this to some of the existing efforts out there that he and Simon and Nick and others have been working on. So how to integrate the two, because one of the things about the geoscience ontology with respect to other timescale efforts is that it allows a connection to the other parts of the geological system, not just the geological time component, which is very useful. And similarly, you know, the encoding of geologic events might look something like this. you know, an event has a certain process and occupies time and has starting and ending components associated with it. And there's a lot of examples out there for how to do that that we've encoded. And similarly with geological structures. Won't get into the details of that too much. Lastly, what we've been doing is not only encoding examples of all the different kinds of things to make sure that we can deal with the variety of geological scenarios that we're trying to represent, but also take advantage of repositories that would then contain this information within a knowledge system and be able to extract them in particular ways. So this is an example of a particular repository built from examples provided by Rachel in the British Geological Survey of geological units, and extracting them from a knowledge database, in this case containing RDF triple stores, and reorganizing them so the information ends up looking like a table rather than the encodings that you saw earlier. So a listing of the units, their component materials, the role played by them, and the proportion of that material within that unit, for example. So while the encoding and representation is thorough, complex, but comprehensive, there are query languages, etc., that can extract components of that in the typically understandable ways for feeding into other systems, such as 3D modeling tools. And I'll just wrap up with some links here to a reference manual for version 1 that's available online, to the release of the ontology as a series of OWL files encoded in the Turtle syntax, published through Zenodo, linked back to the GitHub repository. And I should just add that we have a series of publications in process describing this in a user-friendly way, whereas the reference is a bit of a hardcore description of everything there. But we continue to want to work with others to evaluate these ideas, see how useful they would be. And currently working on some revisions based on existing feedback from individuals for a version 2, which is going to correct some of the logical inconsistencies present in version 1 and make some minor modifications as a result of that to the various code. The other big piece that we have going, though, is we're ready to start integrating this with the existing Loop 3D modeling code. So that's a next big step that we want to move forward on. That involves semantic repositories, working on the semantic repositories and better linking them to the existing 3D modeling code. But that's just one application area for the ontology. There are many others that we'd like to explore. So I think I'll wrap it up there, unless Steve is with us and wants to add anything, and open it up for questions.
Thank you, Boyan. Discussion, please.
It's Nick here. Just a quick statement more than a discussion, which is so we are able to build systems that can express data according to the Loop 3D ontology. That's kind of the deal. And so we have had a couple, Boyan and myself and others have had a couple of goes at exporting data from, say, GeoScience Australia, the stratigraphic units database there, and expressing that in terms of the Loop 3D ontology and actually making that available. If someone can look at the ontology, they can map their data to the ontology, they think they've done a good job, then we can either build a static data set that is that data in that form, or we can export that data into a way that can allow it to be delivered online. But the goal is to export lots of data or to formulate lots of data according to the ontology and then use common queries. So, you can take data in Australia, formulate some fantastic queries on it, and then someone in Italy can reuse those queries on their data if they can map to it. So there'll be this long period of going around the geological agencies, finding data sets that map to some part of the GSO, and of course it's a huge ontology, so some part of every geological data will map to it, and exporting data in that format and then hopefully sharing the queries and things, because it takes a lot of time to work out these rules. And then if you've got a very good query that achieves some outcome, it'd be good to get that reused.
Yeah, thanks, Nick. Yeah, you're building. There's some really good tool building going on there for exporting and using the ontology. But I should say we're still a little bit in early days. We've essentially just built it. Now we're exploring its utility, and no doubt there will be some revisions to be made to see that. So, from a standards process point of view, this is pre-standards type efforts where we're still sorting out how useful things are and where the holes are and trying to patch them.
Very good. More discussion, please.
One of the things I didn't mention, but is an obvious fit, if we're talking about a global knowledge graph eventually for geology, so where all the knowledge of geology that sits in different databases and different knowledge system might at some point be connected together, which is one of the visions of DDE, for example, but is also a vision shared by many other people around the world. It seems to me that we will need some sort of encompassing ontology or group of ontologies that will make that kind of system work. So part of this work is to iterate towards that and start building, this type of global knowledge system that we can eventually draw on. But it's very early days, obviously. So this would fit into that kind of thinking and contribute to it, the GSO ontology.
So Boyan, in order to pursue that objective and to organize ourselves such that we can make efficient progress, would you be able to cite another field that we could learn from in terms of how to structure our activities, whether that be biology or chemistry, or what field comes to mind?
Probably my biology is the most advanced, but really it's subfields of biology. So for instance, there is the gene ontology, for example, which is heavily used. One of the things that made that really happen is the fact that the leading journals required people to post their results. So if they made innovations in knowledge on gene research to publish in the journal, they actually had to contribute the results of their research to the ontology in order for it to be published. So knowledge was no longer resident just in journal papers. It was actually also resident in the ontology that lived alongside the journal paper, for example. And that's probably seen as the biggest win, I would say. There are similar efforts to a lesser degree in different areas, but that's one of the best known, for example. And it's a good example of how your research results as knowledge are also represented for use by the community digitally.
Thank you, Boyan. So let's just have another minute or so of discussion on Boyan's presentation. Who would like to speak? Okay, hearing no one, why don't we say thank you, Boyan? And now we have
The chat box, Harvey.
Go ahead.
The chat box, Harvey.
Oh, Boyan, would you please look at the chat?
Okay, thanks. I see a question from Eric on how do you deal with different or divergent opinions. Well, I would, from an ontological point of view, those are different concepts. So if you have an ontology that is general enough, at some point, those different concepts will map into one of the more general ideas. And so different opinions would simply end up being coexisting concepts in the bigger ontology. They won't, and then you can map particular pieces of information geologically to one or both of those ideas. So you can say this piece of data, actually is an instance of this one concept, but maybe not be an instance of that other because it doesn't apply to this data. And it's a way of matching, in fact, theories to data in that sense. And so I don't see any issues there. Those are just matters of having different concepts in your ontology.
Very good. Anything else in the chat, Boyan?
I see Dahlia, hi Dahlia, asked the question of linked and shared ontologies and also Sparkle endpoints caused me to think of services to link them. Do these exist? I think that's what Nick was answering, that we have some preliminary services that are being created, but it's very early days. And so that's what Nick was discussing. There's some early Australian services there.
And that's it, Boyan?
Yes, foolishly I took those services down just the other day to do a system change. But look, because the ontology has developed, we will reissue those services indicating a newer version of the ontology soon. So the ontology's had a version 1 release, and so the services will be turned back on, performing according to that. And when there's another version of ontology, we'll match that as well. So yeah, sorry, I really should have ensured that they were up for this meeting today. It never quite occurred to me at the time.
Okay,